So I'm going to use this norm as in the rest of the analysis. Now we should know where we are heading. We are heading towards a stationary point. If I'm heading towards a stationary point, what is one of the qualities of the stationary point? How will I identify it? Grad f of x star should be 0, right? We had studied this right in the beginning, that the signature of a stationary point is its gradient is 0, right? So let's keep a note. We should always know where we are heading, otherwise it just looks like random math, right? So at the solution, grad f of x star is equal to 0. Do I have an explicit expression for grad f? We do, right? It's simply qx minus b, right? So qx star minus b is equal to 0. Okay. Right, so this is just an aside that we will use. Now let's get back to what we're interested. What is the distance of the iterate from the solution? But we are going to use the q norm instead of the 2 norm. So what we need to compute is this, right? So we'll just plug in the definition of this norm. I'm going to get xk minus x star transpose q xk minus x star. Okay. If I open this up, how many terms do I expect? 2, 4, 6, 8, how many terms? 4 terms, right? Let's explicitly open it up. Xk transpose qxk is one term, plus x star transpose qx star is another term, and then I have the cross terms. Right. Okay. Let's keep in mind this expression over here. Can I simplify a few of the terms over here? No, I've just opened it differently. The first 2 terms are positive, the next 2 terms are negative, right? So do I see a qx star anywhere in this expression? Is there a qx star hanging out somewhere? There's a qx star hanging out over here. Is there a transpose of that hanging out somewhere? There is a transpose of that also hanging out over here. So this term is going to be b, and therefore this is b transpose, right? If you take transpose of this expression, what will you get? You will get b transpose is equal to x star transpose q. Q is symmetric, so q transpose equal to q. Okay, I have this. Anything else that I can pull out? Can I group some things common? I'm going to put a half over here everywhere. Can I simplify this entire expression of 4 terms in terms of f? Can you see if you can identify an f over here? What was my definition of f? Half x transpose qx minus bx. Am I seeing those terms anywhere? Do I see a f of xk anywhere? What was f of x? Let's write that once again. Half x transpose qx minus b transpose x. Okay, now do I see f of xk anywhere? First term matches b transpose xk. Is that there anywhere? First and which term? Third term. First and third term, if I combine, this is f of xk. If I combine term number 2 and 4, x transpose k, sorry, yeah. So So have I made a mistake anywhere or it's okay? X transpose XK. Yeah, okay. Term 3 and so this is B transpose XK and okay, so have we made a mistake in algebra somewhere? 1, 3 and correct. Half is not for the B's coefficient. Correct. So let's get this out. So half, okay, let's write this down properly. So I'm going to get half of XK transpose QXK and B transpose XK, and this is going to give me minus B transpose XK, right? This is what I've got. So this is, and what is left? Plus half X star Q X star, right? So what is left? Now, can I make somehow, can I write this in terms of f of X star by some algebra, by some clever trick? Is it possible? Yeah. So this is clearly f of xk, right? What about this term? Minus f of this term is minus f of x star. Okay. Why is that? X star, let's see that. X star is Q inverse B. Therefore, okay. I mean, it is correct, but does everyone follow what has happened over here? How this became minus f of x star? So let's try to write it out a little bit more explicitly. We have, what is the solution over here? Qx star is equal to B. Qx star is equal to B. From here, what do we do next? So x star is equal to Q inverse B. Then substitute in the expression of f. Okay, what will I get? Do I get a, and then I'll do the same in the first term, okay? So this is Q inverse B. This is, you want to leave it as it is? B transpose Q inverse transpose. Then, so the Q inverse goes to identity, right? Then what does this become? Half of B transpose Q inverse transpose B, and then that transpose Q is symmetric, so I can get rid of this, right? And then I have a B transpose Q inverse B. Okay, then and then this half and half becomes equal to minus half of B transpose Q inverse B. Okay, I'm still not there yet. I want this expression. What do I do next? Substitute, I can substitute B as Qx star, right? So now if I substitute B equal to Qx star, I'm going to get exactly this expression, right? Right. So little bit of algebra, right? But we get this expression. This is, let's write this as an aside. Okay. So what did let's summarize it over here. Half of this distance, xk minus x star square in the Q norm is equal to f of xk minus f of x star. Okay. Yeah, question. The B xk, that's here. It had there were 2 of them, then they got multiplied by half. So the coefficient became 1. The term number 3 and term number 4, these guys. A transpose B is equal to, I can swap it, B transpose A. That's how I got this. So 3 and 4 combined into this, and the second term is what needed a little bit of algebra to see it is actually f of x star. Anyone having trouble in this step? So it's if you write along as you're watching this, it will make more sense. Otherwise, it just looks like a bad movie. Right. So this is what you get. Now, unfortunately, at this point, the proof is equal to pulling a rabbit out of the hat. There's a lot of hard work done by another scientist. So we're going to write his name over here. It's Lundberger, who takes it from this point. So I've related the distance between between the iterate and the convergent point to the difference of function values. So that's a great simplification. And Lundberger takes this further and says that this norm over here is actually less than equal to this proof is not going to be done in class, but we'll take it on faith. So after relating this norm of the iterate distance to the function values, this is what you get. Now what are, anyone wants to guess what the lambdas are? Eigenvalues of Q. Okay, these are the lambda i's are eigenvalues of Q. Okay. There is a similar question that you will also find in the tutorial about this. Okay, so now this is a very, very useful result, because if I wanted to look at, if you look at the definition of linear convergence, what was the expression that you had? What was the ratio that we had in when we spoke about linear convergence? The ratio of what to what should be less than something. What was it? It was xk, so let's call it delta x, k plus 1 norm divided by delta xk, right? Delta x is xk plus 1 minus x star. That's the meaning. Was what? Less than equal to r, where r was 0 to 1. Does it look like that? Does this expression that we have got, does it look like that? It does look like that. What is my r? Square root of this expression, right? Because I've got the squares on both sides. So r is equal to square root of this lambda n minus lambda 1, lambda n plus lambda 1. Okay. Again, just a quick linear algebra refresher. I've called these the eigenvalues of Q. If I call these the singular values of Q, would I be correct or incorrect? Correct, because for a, not just a square matrix, right? For a positive definite matrix, so obviously which is also symmetric, the eigenvalues and the singular values are identical, right? So I can talk in either terms. Okay. So this proves that convergence, we proved earlier that convergence happens, and now we are saying that convergence is what? Linear. Now this expression over here with the red arrow contains in it actually a lot of intuition. A lot of geometric intuition is contained inside it if you pay attention to it. So remember when we had drawn the zigzag contour of the steepest descent trajectory, remember the zigzag contour? That zigzag contour had happened when I had an elliptical cup, so to speak, right? And we had said that the curvature of the cup is related to the properties of the Hessian. Second order derivatives gives me curvature information. Where is the Hessian over here going to, in this quadratic cost function which I have, the Hessian is going to be what? Q is going to be the Hessian. And what have I got over here? The R term does it have the properties of the Hessian? It directly has the properties of the Hessian, the eigenvalues. Now, if I had a square bowl or a square cup in n dimensions, what would happen to the eigenvalues? They would actually all be the same. No matter which way you approach from, the curvature is the same. So you would have the same eigenvalues. So that was actually a special case. If I have circular contours, right? That means the bowl is actually like a circle in n. It's a bowl in n dimensions, circular in cross section. No matter where you start from, you are going straight into the solution. So you can see that over here. Lambda n is equal to lambda 1. Therefore, what? It becomes 0, right? So the distance between xk plus 1 and x star becomes 0 in one shot. And this theorem is telling us that. So the curve, and on the contrary, if I have a very squished a very squished bowl, so to speak, right? Like a very, very elliptical thing, then lambda 1 and lambda n are going to be very different. So this r term is now going to become larger and larger, right? So that means you may take many steps to arrive at it. No matter how many steps you take, the rate at which these steps are going to go is linear. That is clear from this proof. Okay, yeah, that's a good point. So this was proved under some very restrictive conditions. The first restrictive condition was I assumed quadratic cost function. I assumed convexity. Well, that's okay. I assumed exact line search, right? So the question is, will this work in general for inexact line search? Will it work for non-quadratic cost function? As you will find out in the research literature, people have proved that linear convergence happens even with inexact line searches. But we won't do it here. Those proofs get more and more involved. Yes. Yeah. Leuenberger's proof is in the line of this, but there are several steps over here, so we have just stated the final result over here. But other people have generalized this and shown that even if you do it inexactly, you will still get linear convergence. It's not that linear will become sublinear or something like that. Okay. So this expression that we have over here, lambda n and lambda 1, which could also be written in terms of sigma n and sigma 1. When we were doing a review of linear algebra, we had encountered these two numbers. And what was that? When did we encounter the ratio of sigma n and sigma 1? The condition number, right? So the condition number of Q is simply the maximum singular value by the minimum singular value, which is simply okay. So intuitively, what we are sort of getting from here is that the worse the condition number. Worse means a worse condition number is a high condition number. The best condition number possible is actually for the identity matrix, which is 1. You cannot have a condition number less than 1. So the higher the condition number, the bigger is this ratio, lambda n to lambda 1. And this constant over here is going to get larger and larger, right? As it gets larger and larger, that means you may have to make more and more steps to reach here. Okay. So this is the story with how the gradient descent family of methods work. They converge, and they converge at a linear rate. This convergence we have proven under a restricted set of assumptions, but if, the class notes have proofs for the other methods as well.